It seems that the video I made debunking the idea that both particles reach the end of the track at the same time has caused a stir. A lot of people have seen it. A lot of people have left me comments. Some people have told me they've been misled their whole lives. Some people insult me in the comments, but then there are others who politely ask me for an explanation of why airplanes fly. If that theory fails, please suggest another. We're here today because I'm going to explain how supersonic airplanes fly. Surprisingly, explaining subsonic flight is actually harder. So we're gonna make two videos. In this first one, we're gonna talk about how a supersonic airplane flies, and in a second video, we're gonna talk about how a subsonic airplane flies. To understand why airplanes fly, watch until the end. I'll also show you some simulations. Let's get started. Well, the physics of supersonic flight and subsonic flight is drastically different. Very different because at Mach 1 shock waves start to appear. Yes, the legendary shock waves. Well, just in case there's still someone who doesn't know what Mach 1 is, Mach 1 means you're flying at the same speed that sound travels. And that's why below Mach 1 it's considered subsonic, and above that it's considered supersonic. In this video, as mentioned, we'll focus on supersonic speeds above Mach 1. As I said, the physics is different because shock waves occur. Therefore, the flight of supersonic airplanes is going to have to do with shock waves, as you're probably already imagining. So explaining what a shock wave is happens to be my specialty, so you've come to the right place if you want to understand it. It was explained to me in many different ways, and honestly, none of them convinced me until after reading a lot of things in various places. I think I found the perfect way to explain what a shock wave is. So let's get to it. Alright, what you need to know is that when an object is moving forward, for example my hand right now, it's generating pressure waves, which spread out in all directions. So the particles that are in front of my hand receive those pressure waves, which transmit information that an object is moving forward. Therefore, the particles that are in front of my hand receive that information in the form of pressure waves and know that an object is approaching. Therefore, the particles get ready to move out of the way of the object. However, when an object is moving supersonic, the object is moving faster than the speed at which these pressure waves propagate. Therefore, the particles in front of the object receive no prior warning. They receive no information before the object arrives. Therefore, the particles are normal, undisturbed, and suddenly they feel the object drastically pushing them out of its way. That's the shock wave, and to help you understand, here's the best example. An object moving at subsonic speeds would be this duck, which is moving slower than the waves it generates. Therefore, if I were in the water and this duck was approaching me, what I would feel would be some waves, little by little, and then I would move aside because these waves would push me and the duck would pass by without any problem. But if now the duck goes faster than those waves, we would have this situation where if I am in the water and the duck is approaching me, I don't receive any information that the duck is coming. And suddenly I would be forced to move drastically. That would be the shock wave. All the information, a super push that the duck would be giving to move the things in front of it out of the way. Well, that's exactly what happens in a shock wave. An airplane moving at supersonic speeds, literally, pushes air aside as it moves through. That's the shock wave. Well, shock waves, as I told you, are like a push. The object is pushing the air out of its way, so what it does is compress it against the particles next to it. When air enters a shock wave, pressure rises significantly, which makes sense. The air is just calm, and suddenly it feels a push that compresses it against the particle next to it. And that's why the pressure increases. And in case you didn't understand with that explanation, let me show you with this picture, which I think is splendid. This would simply be a great analogy because we have a skier who would be like the particle, where the skier is going down a slope and suddenly a tree is put in front of him. So what happens is that the skier gets compressed against the tree, crashes into it, but behind him there are more skiers who crash into the skier who got stuck. Compressed against the tree, and so on. That's a shock wave. Particles repeatedly compressing against each other. And something everyone wonders is, why does it sound like an explosion? I've mentioned this before, but I'll repeat it since some haven't seen my previous videos. I'll also link the shock waves playlist for you. The thing is, shock waves sound like explosions, but obviously they're not explosions. What happens is that our ears and brain turn pressure waves into sounds. In reality, sounds don't truly exist. Our brain simply interprets pressure waves as sound. We perceive them as if they were sounds. And so, as I'm telling you, the pressure increases drastically. The air is so calm and suddenly it gets compressed. There, the pressure increases a lot. So for us, it's as if it were an explosion. Our brain tricks us, so to speak. But if you've noticed, the shock wave comes because the object is pushing the air out of its way. But if we had a surface that was parallel to the direction of the air, then this surface wouldn't be generating any disturbance. It doesn't push air aside, just lets it flow over undisturbed, so no shock wave forms. And that's exactly right. A surface parallel to the velocity of the air doesn't generate a shock wave. But the moment we introduce a small disturbance, that disturbance will generate a shock wave because it will be pushing the air out of the way. So as I'm telling you that shock waves greatly increase the pressure, if we could design an object that generates a shock wave underneath but not on top, then due to the pressure difference, there would be more pressure below than above, because the air above wouldn't be affected at all. I mean, its pressure wouldn't change, but below the pressure would increase a lot because of the shock wave, and that would generate lift. That's how supersonic airfoils work. They're diamond shaped because supersonic planes are designed to also fly inverted. Anyway, imagine we have the airfoil like this. On the top, no shockwave forms because of the surface. It is parallel to the air, but on the bottom part, since the air is hitting that wall, it generates a shockwave that increases the pressure and that creates lift. But let me remind you that this difference in pressure is because the airfoil is pushing the air. Because if, for example, we saw this same airfoil at Mach 0.5, well, this airfoil at Mach 0.5 would generate some pressure waves that propagate forward. The air approaching the airfoil senses its presence, adapts to its shape, and flows smoothly past it. Smoothly, so to speak. However, when it goes supersonic, that doesn't happen, because the pressure waves can't propagate forward, so the air comes and suddenly gets pushed by the object. A very interesting thing is that the faster an object goes, that is, the higher the Mach number, the more inclined the shockwave will be. It will be closer to the wall. For example, as the Mach number increases, it becomes more inclined. But these are simulations, not animations. This would actually happen. The shockwave is a push, as I mentioned, and this push is perpendicular to the cone of the shockwave. Basically, the push would go in this direction. So the greater the angle of the shockwave, the more the push will focus on pushing, on compressing the particles that are coming from behind. So the greater the angle of the shockwave, the more it will be compressed. And that's exactly how it is. This is where it all connects, because as I said before, a bigger pressure difference between the bottom and top creates more lift. But the higher the Mach number, the more inclined the shockwave will be. So the lift coefficient will be higher the lower the Mach number is, because the air will be compressed more. Therefore, the pressure difference will be higher, generating more lift. So the lift coefficient will be higher the closer you are to Mach 1, because that's where the shock wave will have the greatest angle, and therefore the air will be compressed more. Therefore, there will be a greater pressure difference between the bottom and the top. And this can be clearly seen with the graphs of the lift coefficient and the drag coefficient, which both increase the closer you get to Mach 1. And the farther you get, the higher the Mach number. For example, Mach 3, both will be lower. The shock wave tilts, because I haven't told you this yet, but of course there is also drag caused by this shock wave. Because if I'm telling you that the shock wave is a push that our airfoil gives to the particles, of course that's going to generate drag. And this is what is known as wave drag, that is drag caused by the shock wave. And as I'm telling you, the greater the angle of the shock wave, the more energy will be focused on compressing the particles. So that's where the most... And that's also why the closer you are to Mach 1, the greater the angle of the shock wave will be, and therefore, the greater the drag. So Junkie, I hope you understood how supersonic airplanes generate lift. This fascinates me. Supersonic flight is definitely what I like most about all aerospace engineering, the idea of being able to understand what a shockwave is. Because at first I thought shockwaves were just the sound of the plane, of the engines, lagging behind, so all the sound would reach you with the shockwave. But no, it has nothing to do with that. An object traveling at supersonic speeds, even without engines, would still create a shockwave perceived as an explosion. It's incredible. Well now, let me know in the comments below, did you already know all this or did I just show you the light? In the next video, I'll explain how subsonic planes fly. This topic is more complex than supersonic flight and sparks more debate. I think my previous explanation was clear, but subsonic flight is much harder to grasp. So well, when we get there. When we reach the impressive number of 1,000 likes on this video, I'll upload the video about why subsonic planes fly. So smash the like button down below if you enjoyed the video, and most importantly, share it with your friends, those who want to understand why an F-18 flies at supersonic speeds. And by the way, if you want to keep learning about this topic, I'll leave here a lecture I gave a few months ago where I explained some misconceptions, things people believe about subsonic flight. That's not the case. I'm genuinely obsessed with supersonic flight. Let me know in the comments if you want me to discuss this more. I could talk about this endlessly, seriously. And actually, I'm planning to make a whole video explaining supersonic profiles. Because if you think you understand how supersonic profiles work just with what I've told you or what you already knew, you have no idea. Because when I started running the simulations, I realized some things I didn't know, and oh man, and there are still things I don't know and have yet to learn. Oh man, that's why this topic blows your mind. I mean, the fact that information travels slower than the object itself, it's just... So anyway, Yankee, I won't keep you any longer. Give it a big like, just reminding you again, if you want to contact me, you can do it through Instagram or LinkedIn. See you in the next video. I'll leave a link here so you can subscribe, and here's one of the best videos on the channel. Yankee, above all, always science and facts.